There is something sitting in your lungs right now that has a history so old it makes your entire civilization look like a rounding error. You breathe in, and some of those atoms, not all of them, but some, have been through processes that would make your head spin if you really stopped to think about them. Not in a vague, poetic sense. I mean literally, mathematically, provably, those atoms have been inside the body of an animal that walked this earth 65 million years ago. And I want to show you exactly how we know that, because the physics behind it is one of the most beautiful things I have ever come across. Let me start with something simple. An atom of oxygen. You just breathed one in. It is sitting in your bloodstream right now, being carried around, doing its job. Now here's the question nobody asks at parties. Where was that atom before it was in your lungs? Well, it was floating around in the atmosphere for a while, and before that it was in a plant, part of some molecule doing photosynthesis, and before that it was in the ocean, and before that it was inside a rock, and before that, well, here's where it gets interesting, because we can actually trace this backward in a way that is not just guessing, it is physics. The first thing you need to understand is what an atom actually is, not the cartoon version, the real thing. An atom is mostly empty space, genuinely. If you took the nucleus of a hydrogen atom and made it the size of a marble, the electron cloud around it would extend to roughly the size of a football stadium, what you call a solid object, your hand, the floor, the chair you are sitting in. That is really just a collection of electrical forces between nuclei and electrons that are spaced almost impossibly far apart relative to their own size. When you shake hands with someone, your atoms never actually touch their atoms. The electrons repel before they can get that close. You are always, your whole life, a fraction of a nanometer away from directly touching anything. Now that might seem like a detour, but it is not, because this emptiness is the key to understanding why atoms are so spectacularly immortal. An atom does not wear out, it does not get tired, it does not decay just from being used. A carbon atom that existed 3 billion years ago is chemically identical to a carbon atom that formed last Tuesday. There is no arrow of time written on an atom. No wear marks, no aging, no degradation from ordinary chemistry. When atoms combine into molecules and molecules break apart, the atoms themselves remain completely intact. This is the foundation of everything I'm going to tell you. Now let us talk about conservation. In physics, we have these beautiful laws, and among the most powerful ones are conservation laws. Conservation of energy, conservation of mass for ordinary chemical reactions, conservation of electric charge. These are not suggestions, they are not approximations. They are things that, as far as we can tell after centuries of incredibly careful experiment, never get violated, not once, ever. And conservation of matter in ordinary chemistry tells you that atoms are not created or destroyed in the kind of processes that make up biology. When a dinosaur breathes, it takes atoms from the air. When it eats, it takes atoms from food. Those atoms become part of its body, incorporated into proteins and fats and bones and blood. And then when that dinosaur dies, those atoms go somewhere. They do not vanish. They cannot vanish. They get released back into the environment through decomposition, through oxidation, through 1,000 slow chemical reactions, but every single one of those atoms is still around, somewhere. 65 million years is a long time, but it is not long enough for atoms to disappear through ordinary chemistry. Not remotely long enough. The dinosaur dies, it decomposes, the carbon goes into the soil, and eventually the atmosphere as carbon dioxide. The nitrogen cycles through bacteria and soil and plants. The oxygen does its own cycling. The atoms spread out, they dilute, they mix. They travel through ocean currents and wind patterns and geological processes. Over 65 million years those atoms have been distributed across the entire planet, into every ocean, every continent, every cubic meter of atmosphere. Here is where the counting argument becomes devastating in the most wonderful way. Let me put some numbers on this for you, rough numbers, but the physics is solid. The human body contains somewhere around 7 times 10 to the 27th atoms. That is a 7 followed by 27 zeros. An absolutely staggering number. Now, the mass of all the dinosaurs that ever lived, all species across roughly 165 million years of dinosaur dominance, is genuinely hard to estimate, but paleontologists and geochemists have made attempts. When you work through the numbers, accounting for population sizes and body masses and generation times, you end up with a rough total biomass that, when spread across the atoms available in the biosphere and atmosphere and ocean and upper crust, leads to a beautiful statistical conclusion. The mixing is thorough enough and the number of atoms is large enough that essentially every breath you take contains atoms that were once inside a dinosaur. Actually, let me give you a cleaner version of this argument because I think it is more honest and more striking. The atmosphere contains roughly 10 to the 44 atoms, give or take. The total number of atoms that have passed through all dinosaur bodies during the entire Mesozoic era is, by reasonable estimation, somewhere around 10 to the 41 or 42 atoms. Do you see what that means? It means something like 1 in every 1,000 to 10,000 atmospheric atoms has been inside a dinosaur at some point. And in every breath you take, you inhale about 10 to the 22 atoms. So the expected number of former dinosaur atoms in each breath is somewhere between 10 to the 18th and 10 to the 19th. That is between a billion billion and 10 billion billion atoms per breath, not per lifetime, per breath, each one. Now I want to address something that always comes up when I explain this kind of thing. People say, well, Feynman, maybe those atoms got locked up in rock. Maybe they are at the bottom of the ocean where we cannot breathe them. And that is a fair point worth taking seriously. Geological sequestration is real. Some fraction of ancient carbon does end up in limestone or coal or deep ocean sediment. But here is the thing, geological processes are not static. Carbon that gets locked in rock gets released by volcanism and weathering over millions of years. The carbon cycle, the nitrogen cycle, the water cycle, these are not just biological phenomena. They are planetary scale circulation systems that, over tens of millions of years, turn over the accessible reservoir of atoms quite thoroughly. The mixing is not perfect, no physicist would claim it is perfect, but it is thorough enough that the statistical argument I just walked you through holds up. And I want to be precise about what I mean by thorough. I am not saying every specific atom from every specific dinosaur is evenly distributed. I am saying the distribution is random and widespread enough that the sheer number of atoms in your lungs guarantees by basic probability that some are former dinosaurs. It is the same kind of argument you use when I tell you that the glass of water you are drinking right now contains molecules that passed through the kidneys of Julius Caesar. That calculation was done carefully. The mixing time for water in the global water cycle is well understood, and it comes out the same way. You are recycled Caesar. You are recycled dinosaur. You are made of atoms that have been through extraordinary adventures before they found their way to you. Let me push this even further because we have not gotten to the really dizzying part yet. Those oxygen atoms in your lungs right now, some of them were forged in a star that died before our sun was even born. The oxygen in the universe did not come from the Big Bang. The Big Bang produced hydrogen, helium, and trace amounts of lithium. Everything heavier than that, every carbon atom, every oxygen atom, every iron atom in your blood was cooked up inside a star through nuclear fusion. A star lives its life fusing lighter elements into heavier ones. And when a massive star reaches the end of its fuel supply, it does not quietly go out. It explodes, a supernova, and it scatters all those heavy atoms across space. Some of those atoms ended up in the cloud of gas and dust that collapsed to form our solar system 4.5 billion years ago. So the atom of oxygen sitting in your lung right now has a biography that goes something like this. It was created inside a star that died roughly 5 to 8 billion years ago. It drifted through interstellar space for hundreds of millions of years. It got incorporated into the solar nebula and eventually into the early Earth. For billions of years, it cycled through the geology and chemistry of a young planet. It eventually became part of the oxygen-rich atmosphere that life created. At some point during the Mesozoic era, it got breathed in by an animal the size of a bus, spent some time as part of a molecule of hemoglobin or carbon dioxide inside a creature that has been extinct for longer than there have been primates on Earth. It got released back into the atmosphere. It cycled through plants and oceans and ice ages and volcanic eruptions. And now it is in you. That atom is 5 billion years old and it has never once complained about it. It does not know what it has been through. It has no memory. It is just an atom obeying the same quantum mechanical rules it has always obeyed, completely indifferent to its own history. And yet, here you are, a collection of atoms that have been through this extraordinary journey, suddenly curious about where they have been. The universe spent 5 billion years arranging atoms so that some of them could sit here and wonder about what they are made of. The physics that makes all of this possible is really the physics of conservation and mixing. You conserve atoms through chemistry. You mix them through physical processes. You wait long enough, and the result is that the sharp boundary between you and the ancient world dissolves completely. There is no membrane between you and the Cretaceous. There's no wall between the atoms in your body and the atoms that were once Tyrannosaurus rex. The separation between the living and the ancient is just a matter of where the atoms are right now, not what they fundamentally are. I find this genuinely wonderful, and not in a wishy-washy way. I mean it in the specific sense that understanding this requires you to really grasp what atoms are, what conservation laws mean, what statistical mixing looks like over geological time, and what the nuclear processes inside stars produce. Each of those is a beautiful piece of physics on its own. When you put them together, you get this picture of a deeply interconnected physical world where the concept of sharp boundaries between self and non-self, between ancient and modern, between the living and the long dead, just breaks down, not poetically, physically, mathematically. You are not a separate thing from the history of this planet. You are a temporary, local concentration of atoms that have been everywhere, and the breath you just took carried a few billion of them in from the outside world, some with histories that would fill books, and in a few seconds you were going to breathe them back out again, sending them off to the next phase of their long journey.